Okay, so let's consider this one here. 1 over 1 plus e to the x plus e to the minus x. This is actually a version of the hyperbolic cosecant. Because you look here at our hyperbolic cotangent. Of course, we do the reciprocal of that. We'd have 2 over e to the t plus e to the minus t. Of course, we're losing the 2. That's just a constant. So the hyperbolic cosecant will be 2 over e to the t plus e to the minus t. And so we're really, in a sense here, looking at an integral that's related to the hyperbolic cosecant. But I'm not going to think about it that way. I'm not going to think about it in terms of that. What I'm going to realize is that e to the minus x there, first of all, kind of like, where do I go from here, first of all? Right? Can't really use a substitution. Can't let u be e to the x or anything like that because I don't have an e to the x up on top to deal with the derivative. So what I realize here, or what I try to do here, is first I have an e to the minus x there. Remember, when you have something to a minus power, that means it's going to really be in the bottom. So this is really e to the x plus 1 over e to the x plus 1 over e to the x. And what that creates for us here is a complex fraction. Right? We have one fraction inside of the bigger fraction. And for us, that's a good thing to see because that gives us an idea of something we can try. Now, a lot of times with integrals, when you're trying to work an integral out, it's let's try something and see if it works. Right? Let's try something and see if it works. So here, since I have this fraction inside of the bigger fraction, I'm going to get rid of my complex fraction, right? Which is what it means when you have a fraction inside of a bigger fraction. And we do that by multiplying both top and bottom by my common denominator. So inside the integral here, I'm going to multiply basically by 1. E to the x over e to the x. I'm going to multiply by 1 across the top and across the bottom. Okay. And hopefully that will get me somewhere where we can make some progress. Okay. So that's what we're hoping for here. So multiplying through by e to the x on the top, I'll just have integral of e to the x. And then in the bottom, when I multiply by e to the x, I'm going to have e to the x times e to the x, which will be e to the, careful here, 2x, not e to the x squared. Right? Remember, when you multiply, you add exponents. And then e to the x times 1 over e to the x, they cancel out. Okay. So now I have something that's a little bit easier to work with, at least can make some progress. So my first thought might be to let u be this denominator here. Right. That might be my first thought. Reasonable thought. Problem is, when you do the derivative of that, you'd be doing the derivative of e to the 2x, which would be 2 times e to the 2x. Unfortunately, I don't have an e to the 2x on top. The 2 is not a problem, but the fact that I'm missing an e to the 2x, I have an e to the x up there, but not an e to the 2x. Okay. Then a little light bulb goes off in my head. It says, hey, what if I write that e to the x squared, or e to the 2x, as e to the x squared plus 1? Well, then I can let u be e to the x. Then du would simply be e to the x dx, which is what I already have on the top. Right? So I let u become that e to the x on the inside. And then I can take the e to the x on the top along with the dx, and that makes my du. And so now I can carry the substitution through and change from u over to, from e over to u. Right? And that gets me to this integral of 1 over u squared plus 1 du. Okay. Now, how does that help me? Well, you say, well, how do I integrate that? I can't let v, I guess, my new variable, u be u squared plus 1. How does that help me? Well, for now, we have to just remember that the derivative of the inverse tangent function is 1 over 1 plus x squared. Okay. For now, we just have to remember that. So this is actually an inverse tangent. This is actually an inverse tangent. So we just have to remember that derivative. In this chapter, we are going to develop techniques that will let us deal with a u squared plus something without having to completely fit it into the inverse tangent or inverse sine or inverse secant functions. But that'll be a little later, a few sections from now. For now, we just have to remember this. And so we're able to then carry this through and say, hey, this will be the inverse tangent of u plus a constant, but u is equal to e to the x. So this will be the inverse tangent of e to the x plus a constant. Okay, so that is actually the answer for this problem here. It's actually the integral of this thing happens to be the inverse tangent of e to the x plus a constant.